Welcome, and today we're going to start the next topic in the next chapter, if you're in my class, and that is going to be on the normal distribution. And so the normal distribution is a continuous distribution, so we're continuing with our continuous distributions talk. And this distribution is the single most used distribution out there. And it is also the most abused distribution out there. And so the normal distribution comes up in all sorts of applications. In science, in business, in nursing, in economics, even in mathematics, of course. Also, some professors may use the normal distribution in assigning grades for students. That is common, especially if you have a large class. Okay, we're going to talk about a little bit of stuff like that. But the normal distribution is so common that for the rest of this class and the rest of the topics, the normal distribution will be the distribution that we want to use the vast majority of the time. Okay? So what is the normal distribution? Well, the normal distribution is a bell-shaped and symmetric distribution. It is a distribution that has two parameters. So remember, the parameters of a distribution describe, are basically the two thing, or the, well, how do I want to say this? Remember that depending on the distribution, the parameters completely describe that distribution, right? So in the binomial distribution, what were the parameters? It was the sample size and the probability of a success on a single trial, right? So we needed to know both of those parameters in order to completely describe and calculate the mean, the standard deviation variance, to calculate probabilities, and so on and so forth, right? Well, the two parameters, there are two of them for the normal distribution, that we need to know in order to completely describe the distribution is the mean, mu, and the standard deviation, sigma. Okay? If we know both of those parameters, then we know and can describe the normal distribution. So let's start with that. So the normal distribution is denoted as, again, x is a random variable, right? So here we have x has a distribution that's normal, so we use capital N. And then inside the parentheses are the two parameters. And we're always going to list the mean, the population mean, followed by the population standard deviation. So it'll always going to be mu, comma, sigma. And that's what we're going to do. So this is how we denote when we have a random variable that has a normal distribution. Okay? So now what is it going to look like? Well, it's bell-shaped and symmetric, right? So we know that it's from our previous discussion. Bell-shaped and symmetric, which means what can we use? The empirical rule. Remember that? So since the normal distribution is a bell-shaped and symmetric distribution, we can use the empirical rule. Okay. Also, what are we going to also look at? Now we're going to bring back z-scores. Remember those z-scores? So now we're going to talk about how z-scores are related to the normal distribution. Okay? So remember when we talked about z-scores before, you just needed to know how to calculate them and what the z-score stands for. That represents the number of standard deviations above or below the mean a particular value lies. Okay? So now we're going to go into, hey, we can use the empirical rule, but also, more importantly, we're going to see how z-scores are used and where those come in. Okay? So now, with this in mind, we know that we're going to have a curve that looks something like this. And so where's the mean? We know it's going to be in the middle, so mu is in the middle, and it's going to have a standard deviation equal to sigma. And so we know that if we use the empirical rule, we're going to get something like this. So we're going to have mu plus sigma, mu plus 2 times sigma, and mu plus 3 times sigma, right? Or if we just say sigma, 2 sigma, and 3 sigma, right? And then if we go below, then this is going to be mu minus sigma, mu minus 2 times sigma, and then mu minus 3 times sigma, or we could just write negative sigma, negative 2 sigma, and negative 3 sigma, okay, to represent the same thing, okay? So now, here's the situation we have here, right? And if we use the empirical rule, remember, so we know that between these two values is going to be 68% of the data, and between these two values will be approximately 95% of the values, and then between these two values, it'll be up to 99.7%. Okay? Now, we're going to relate these two values based on what the normal distribution gives us, but we'll talk about that in a moment. But realize that since it's bell-shaped and symmetric, we can always use the empirical rule. Okay? So now, how does this relate to z-scores? Well, remember what we use z-scores for, right? We could use a z-score if we had a bell-shaped and symmetric distribution, and we could use this z-score to tell us how far as number of standard deviations, a particular value is above or below the mean. And then we also could use z-scores to compare values, right? If we have two different values from two different populations that are bell-shaped and symmetric, we could calculate the z-score for each one of those values and then see which one is more extreme or which one is higher or lower, things like that. Well, why is it the case? Well, this is where the normal distribution is going to shed some light on this, okay? So remember, the z-score formula was what? Z is equal to the observed value minus the mean divided by the standard deviation, right? That's the formula that we use. Well, let me do this. Oh, I don't like that. I don't like that one either. I'm picky. That's good enough. So now, since I can take any bell-shaped symmetric curve and I can calculate a z-score, let's just apply it to normal, right? So that means any normal distribution, I can calculate a z-score for any value of x on the normal distribution, right? So this is x, right? So x increases going that way, right? So on the number line, so we have x here, right? So now I can take any value of x on a normal distribution and convert it into a z-score. Well, if I do that for every single value, well, I'm going to get a similar distribution, but not a distribution of x, a distribution of z. And so this introduces what we call the standard normal distribution. Because if I can calculate the z value, right, for each one of these, well, what I'm going to end up with is a similar distribution, another normal distribution, but it's not a distribution of x, it's going to be a distribution of z. So what I'm going to end up getting is I'm going to get a distribution of z, which is normal. Well, what happens here? Well, if I convert mu, what does mu convert to? Well, it'll be mu minus mu, which is 0, so z becomes 0. Well, what happens to mu? It becomes 0. And then what happens to this value here? Mu minus sigma. Well, what I'm going to end up getting is -1. And then here, at 2 standard deviations, -2. And 3 standard deviations, -3. Remember z-scores? So this is 1 standard deviation below the mean, 2 standard deviations below the mean, and 3 standard deviations below the mean. And then likewise, if I do the same calculation, what am I going to get? I'm going to get a normal curve where I'm going to get a +1, 2, and 3. So now what happens? I get a formula that converts any normal distribution into the standard normal. The standard normal distribution. That's where the z-score formula fits. Okay? So now, how is this going to help us? This is going to help us tremendously later on when we're talking about confidence intervals. We're going to talk about hypothesis testing. We're going to talk about probability. The z-score is going to help us figure out those things. Percentiles, you name it. Okay? So now I've got a formula here. Again, now I can use the empirical rule because now, just like you would think, 68% of the data will fall within 1 standard deviation of the mean, right? And then we have 95% between 2 standard deviations, and then 99.7% within 3 standard deviations. So you can still use the empirical rule, okay? And this is what we're going to use in every case where, let's say we want to make an apples-to-apples comparison. The easiest way is to put it on the standard normal curve, okay? So now remember, the main thing is always remember that the standard normal curve, always, this is always the case. Here's the main thing, and I get a lot of students that will get confused by this. They'll have a problem on the homework, and it'll say, hey, I want you to find the probability of z being less than 1.3. Okay, so let's say I have this. So I'll say, hey, find the probability of z being less than 1.3. And they'll email me or they'll ask, well, I don't know how to get this probability. I don't know what the distribution is, or I don't have enough information. And my answer is, yes, you do. If you understand that they're giving you a z-score, and anytime you're given a z-score, it implies that you're talking about what? The z distribution, or the standard normal distribution. And anytime you're dealing with the probability of z, well, remember, in order to calculate a probability, we need to know the distribution. Well, we do know the distribution. It's this. It's 0, 1, right? A mean of 0 and a standard deviation of 1. So yes, what would we use? As you'll find out, we can get this easily. So remember, the main thing is anytime you're talking about z, or talking about probability of z, or probability, or looking for a z-score, you know that you're talking about a standard normal distribution. And so we know that all z-scores are normal with a mean of 0 and a standard deviation of 1. So always remember that, okay? That's all the information you need to know, okay? Because you know the parameters, 0 and 1, okay? So now, Okay, so another thing I want to talk about is the PDF function. Okay, just like with any other continuous distribution, the PDF function is useless in telling us anything about probability because the probability of any value is 0. Okay, so the PDF function, again, tells us what the shape of the distribution looks like, but it doesn't tell us anything else, okay, that's useful. Okay, so here's the thing. This is the formula for the PDF. So again, this is the function, f of x, right? So this is the function of the distribution, f of x. Excuse me. Let me write it this way. So the function, the PDF function for a normal distribution is e to the negative x minus mu squared. So all the squared deviation, right, of whatever your x value is. Negative that divided by the standard deviation. Then that whole thing is divided by the number sigma divided by the square root of 2 pi. Okay, so this is the formula. Now this is the PDF function. Okay, now the CDF function. Well, in the normal case, there is no specific CDF function. So there is no formula for calculating cumulative probability. So the probability that x is less than or equal to some value doesn't exist as a formula, because in order to get the formula, we would have to use calculus and integrate that. Well, the problem is that is not something that we can integrate. Okay, so it's not integrable. Okay, meaning we can't use any formulas. So what is the workaround? We have to use what's called numerical analysis. We have to use approximations. So before the advent of the calculator, we used tables. So I'm going to show you how to use a table to calculate a probability, but I'm also going to show you how to use the calculator. And the calculator will be the most important thing because it's a lot easier to use nowadays than the table. In fact, I use the calculator for pretty much all of it. I can use the tables. I did all my work when I was a grad student using tables. We didn't use any graphing calculators, even though we had graphing calculators. We just didn't use them. But now I use the graphing calculator for all these, and I'll show you what functions to use. But keep in mind that the CDF function does not exist as far as a formula, okay? But I'll show you the function on your calculator that will also give you the answer, okay? But I'm also going to show you how to use the table, okay? So now, let's see here. Anything else? Okay, let's do an example. So now, let's practice taking a normal distribution and calculating z-scores. So let's say let's see here. Let's see what I want to do. So for example, if I say I have x, and x is normal with a mean of 12 and a standard deviation of 3. So here's another thing. With the notation, the mean, the population mean mu, is always listed first in the parameters. Just remember, order matters when you write these out, okay? So here's what we have. So let's say we have an x value, and let's say x is equal to 1. And so we want to know, hey, what's the z-score associated when we have an x equal to 1? Now, so this is just using the z-score formula. Why? Because we know that a normal distribution is bell-shaped and symmetric, so we know that the z-scores are normally distributed. So we can use the conversion, right? So what we're going to do is we're going to convert this x value to a z-score using the z-score formula. Because what are we going to do? We're going to convert using the z-score formula from a normal distribution of x, right, to a z distribution 0, 1. That's all we're doing. Think of it that way. We're transforming this normal distribution into the standard normal distribution. So we're taking the x value and we're going to convert it to a z-score. That's kind of what's going on here. So with the z-score, it's going to be the observed value, which is 1, minus the mean, oops, sorry, wrong one, minus the mean, which is 12, divided by the standard deviation, which is 3. And so what do we get? Well, we get a negative number, which makes sense because 1 is definitely less than 12. And so now, what do we get? We get negative 11 over 3. And so what do we get? We get, this is going to be 3, negative 3.67. And so that's the z-score. That's it. Okay? So now we know that a 1 on this distribution is equivalent to a negative 3.67 on the standard normal distribution. That's it. Okay. Here's another example. It says, suppose we have this situation. It says some doctors believe that a person can lose 5 pounds on average in a month by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution. And let x equal the amount of weight a person loses in a month in pounds. Use a standard deviation of 2 pounds. So here's what we're doing, right? We're assuming that weight loss is normally distributed with an average of what? What do they believe the average person loses in a month? If they're exercising consistently and they reduce their fat intake? 5 pounds. And what's the standard deviation that they tell us? 2 pounds. So this is the information they give us. Now, it says, suppose a person lost 10 pounds in a month. So let's say x equals 2 pounds. Or no, 10 pounds. Now rewrite. So x is 10 pounds. They lost 10 pounds in a month. How many standard deviations away from the mean is 10 pounds? Well, what's the standard deviation? 2. How many 2's go into 10 pounds? 5. So 10 pounds is how many standard deviations, or excuse me, how many standard deviations above what? The mean. So let me scratch that. 10 pounds is how many pounds he lost. What's the average? 5. How many pounds above the average is 10? 5 pounds. How many standard deviations go into 5 pounds? How many? 2.5, right? So how many standard deviations above the average is 10 pounds? 2.5 standard deviations. But let's calculate it. So now, if I want to transform this into the number of standard deviations, right, z-score, right? How many standard deviations above the mean is 10 pounds? That's a z-score. So z equals x minus mu divided by sigma. Well, what's x? 10. What's mu? 5. What's sigma? 2. And so what do we get? We get 5 over 2, or 2.5. That's it. Now, suppose a person gained 3 pounds. So in other words, negative weight loss. Then z is going to equal what? So in this case here, x is what? He gained 10 pounds. Or excuse me, 3 pounds. So in other words, if x is the amount of weight lost, then if he gained 3 pounds, it would be negative 3. So in other words, in this case here, z is going to equal the observed value negative 3 minus what? 5 divided by 2. And so what would the z-score be for this one? Well, what are we going to get? We're going to get negative 8 over 2, which is negative 4. So if you lost, or excuse me, if you gained 3 pounds, and again, this is under the assumption that you reduce your fat intake and you're exercising consistently, that if you gained 3 pounds, that would have a z-score that would be 4 standard deviations below the mean. So if you remember topic discussion about outliers in chapter 2. How many standard deviations below the mean or above the mean does the value have to be in order to be considered an outlier? 3 standard deviations, right? This is definitely an outlier, right? You wouldn't expect by a long shot that somebody would gain weight if they reduced their fat intake and was exercising, right? You wouldn't expect somebody to gain weight in a month. Okay? Okay, so let's see here. Okay, let's look at this one. Let's say we have this example here. It says the mean height of 15, 18-year-old males from Chile from 2009 to 2010 was 170 centimeters with a standard deviation of 6.28 centimeters. Male heights are known to follow a normal distribution. So what do we know? Well, if we use x, so here x represents heights of Chilean males, right, from 2009 to 2010. We know that x is normal with what mean? Well, 170 centimeters and a standard deviation of 6.28 centimeters. Okay, so here's what we know. It says suppose a 18-year-old male from Chile was 168 centimeters tall from 2009 to 2010. Calculate and interpret the z-score for this individual. So let's say that we have a random variable, we have a height of a male, 15 to 18 years old, and his height was 168 centimeters. Okay, so what's the z-score? Well, the z-score would be 168 minus the mean, which is 170, divided by the standard deviation. And so what's the z-score that we get? Well, let's figure it out. So it's going to be 168 minus 170 divided by 6.28. And we get negative 0.32. Okay, that's our z-score. Okay, so remember, this is a z-score. So what does that z-score mean? It means that his height is about 0.32 or about 32 hundredths of a standard deviation below the mean. So not very far below the mean at all. Okay? That's what that means. Okay? So now here's the other part of the question. It says suppose that the height of a 15 to 18-year-old male from Chile from 2009 to 2010 has a z-score of 1.27. So now, here, we're supposing, hey, the z-score is 1.27. What is the height of this Chilean? Well, let's figure it out. Well, we're still going to use the z-score formula here, right? So let's just write the z-score formula and fill in what we know. Well, we know that this individual has a z-score of 1.27, right? So we know this. We also know the mean, and we also know the standard deviation. What we don't know is the height, which is what we're looking for. So we can use the z-score formula to find x, the height. So in other words, we're going to solve this for height. So x equals z times sigma plus mu. And so if we just plug and chug, what do we know? We got 1.27 times sigma, which is 6.28. And we're going to add that to the mean, which is 170. And so what do we get? We get 177.98 centimeters as the height of this Chilean male. And that's it. And so now we have a way where, hey, if we know we have a distribution, right, we know that it's normal, we can use that distribution not only to find a z-score, but to find an x value given a z-score. So we can go either direction now. Okay? Okay, so now, let's see, we talked about the empirical rule. Okay, so now, let's do this. Okay, so now, here are the actual approximations for a normal distribution related to the empirical rule. Now, let's see here. Okay, so here's an example. Let's say we have in 2012 1,664,479 students took the SAT exam. The distribution of scores in the verbal section of the SAT had a mean of 496 and a standard deviation of 114. Let X be an SAT exam verbal section score in 2012. Then what we have is X, which is the verbal scores, has a normal distribution with a mean of 496 and a standard deviation of 114. Now, if we have two different scores, we know which one is going to be more extreme, right? So if we have this information and I give you two different scores, then all you have to do is convert these to z-scores, and you know how much more or how many standard deviations each one is from the mean. In this case, below the mean, right? So in this case, we would do a z-score 1 is going to equal 325 minus 496 divided by 114. Okay, and so what is that value going to be? Negative 1.5. And this one is going to give us a z-score, z sub 2, let's say, is going to be 366 minus 496 over 114. And so that z-score we're going to get is going to be negative 1.14. Now, obviously we know that the person did better on this exam, right? But if we wanted to look at the standard deviations, then we know that this person did 1.5 standard deviations below the mean, and this score is 1.14 standard deviations below the mean. This one's further away from the mean below than this one, which means that this one is the better score, okay? Which again makes sense because he got a higher score here. So he should be closer to the mean, which makes sense based on our z-scores, okay? So let's see here. Now, let's see if we can use the empirical rule, and let's use this. Let's say we have x is normal with 496 and 114. And let's now use the empirical rule based on the normal curve. So we know the mean is going to be at 496, right? And now all we have to do is use the standard deviation to figure out where the cutoffs are, right? And so we're going to do the same thing over on this side. And so what do we have? 496 plus 114, right? So if we add 114 to here, what do we get? Well, we get 610, right? And if we add 114 here, we get to here, which is what? We get 724. And then if we add 114 again, what do we get? We get 838. And then if we subtract 114 here, what do we get? We get 382. And then if we subtract 114 again, we get 268. And then if we add, subtract 114 again, we get 154. And then now we can fill in the pieces using the empirical rule. So we know that from 382 to 610, 68% of all the scores should fall between those two numbers. And if we go out to 2 standard deviations, so we know that between a score of 268 and a score of 724, 95% of all the scores should fall between those two numbers. And then we also know that from 154 to 838 should contain 99.7% of all the SAT scores. Okay? And furthermore, remember, we can then fill in all these pieces because we know that this has to be 0.15, 2.35, 13.5, and then 34, and then 34, 13.5, 2.35, 0.15. Okay? And that's it. And now we can do the same thing. Now that we have that it's normal, we can use the empirical rule to help us answer questions. Okay? So right back to what we talked about in chapter 2. Only applied to the normal. Why? Because the normal is bell-shaped and symmetric. Okay? Okay, good. So now, that's where we're going to stop today. And then next time, we're going to actually go on and we're going to start talking about applications for the normal distribution. How do we use it to find probabilities and those sorts of things. And it all requires either using a table or using the calculator, as you'll see. So until next time, I'll see you then. Have a good day.